Hello, fellow Army signalers. I'm Dr. Kelly Carter, and I'm a data scientist with CACI International. I work to bring artificial intelligence solutions to federal clients. I'm here today to talk to you about explainable AI and why it matters. I'll be using two examples that correlate to military AI use. One is a computer vision example, and the other is an automated decision-making process. Did you ever have that trusted teammate that couldn't tell you why they did the things they did? That one go-to person who had your back, was always there to give you a great solution, but who couldn't ever tell you why? Probably not. That's because trust and explainability go hand in hand. If we're willing to let artificial intelligence work on some of the military's most pressing problems, intelligence, targeting, cyber effects, and command and control, it should be more than a black box. Black boxes don't give us explanation. There's no proof behind their answers, and we're expected just to push the I believe button. We can demand answers, and yet we don't. In a moment when I discuss our examples, we'll show that when the answers and explanations behind them are demanded, it makes a difference. When we dig for proof, the proof is surprising and reveals exactly why we need to have the explanations. One example is an algorithm that uses computer vision to predict pneumonia based on chest scans. Computer vision is a type of AI that's widely used in the military on everything from satellite images to vehicle license plates. The second example, an automated decision-making process, is also widely used. In our example today, it's used through the correctional institutions. We should know why the ADMs recommend the things they do. In the correctional institutions, they have very real consequences on people's lives. And yet AI is flawed. The biases can be profound and still go undetected. Just so we're all on the same sheet of music, let's peer inside an AI black box. This is an example of a neural network. On the left, you'll see the input layer, and on the right is the output layer. In the middle are the hidden layers that perform the analytics. In our medical example, the model is trained by feeding in chest x-rays, both normal and diseased, to the input layer. Then they're analyzed through the hidden layer, and the outcome is put out by the output layer. Once trained, the model can view images and give a diagnosis with a percentage confidence level. But the radiologist was not satisfied with the black box answer, here seen as 5%. They asked what the AI was basing the decision on, so heat maps were added. Heat maps were the analytical tool to explain what the AI was doing. So here you'll see side-by-side images of the chest x-ray and the heat map. The heat map will indicate negative to positive, the areas that most contributed to the diagnosis or likelihood that the AI came up with. On the left, you'll see the chest scan, the areas where the radiologist or the physician would say these areas are likely to have pneumonia. So let's go to the corresponding areas on the heat map. You'll see that those areas, interestingly enough, have negative values. So they did not contribute to the AI getting it right. What did? So you'll notice yellow circles have 2.5, 2.6, 2.1, very high positive values contributing towards the diagnosis of pneumonia. Well, how could that be? It's the marginal data. The model may have learned that this particular machine or this particular radiologist using this machine had a more likely tendency to diagnose pneumonia. What is shown is the framing and the metadata. Perhaps it was a particular ward or a particular person, but those were the things that led the AI model to the diagnosis. Now let's look at another example. In this particular example, there's a 2.4% likelihood that this individual has pneumonia. Where on the chest scan would the radiologist look? Here it's circled in black as potentially having disease, but the corresponding area on the heat map again has negative values, which is not consistent with the positive diagnosis of pneumonia. Shown circled in yellow are the words portable and the markers for the individual machine that was used. Since portable scanners are often used when patients are too ill to be transported to a machine, there's some validity in considering this information. However, a classic definition of predicting disease is based on the lungs alone, from the scan itself, not the marginal metadata that this model was using. Now, this does point to the fact that the AI model is making correlations, and while some of them are valid, they're not intended nor necessarily desired. And this can be especially troubling if the model itself is missing the very areas in the lungs that are diseased. In our third example, you see a positive prediction for pneumonia of 5.7%, which is higher than our other two examples. And shown in the black circles on the left and the corresponding heat map are high values for areas that may be diseased in the lungs. But what is also reflected in the heat map, as you can see in the yellow circles, is the model is still giving high weights to the marginal data of portable. Clearly, these three examples indicate that the model is making correlation to disease based on factors that are other than conditions of the lungs themselves. And this is exactly why we need explainability in AI. We must be careful as to exactly what variables are considered and what variables should be considered. Let's switch now to another illustration, that of aiding our criminal justice system in predicting which inmates should be paroled and which defendants should be given harsh sentences. This is a predictive analytics that's automated decision-making systems. These can correlate to cyber and targeting use cases in the military. COMPASS, which stands for Correctional Offender Management Profiling for Alternative Sanctions, is a decision assistance tool that's widely used in 4 states, including California and Florida, and similar algorithms are used across the country. The idea behind the algorithm is to predict recidivism, and it's based on 137 factors according to the vendor. Now, some of the factors are questions that the person would answer, like, were your parents ever incarcerated? Did you get into fights when you were in school? But other factors are a matter of criminal records. However, upon a further analysis in 2018, only 6 factors were actually used in forming the predictions. While race was not directly considered in COMPASS, the COMPASS algorithm has largely been cited as having a racial bias. The problem with evaluating an algorithm like this is that it's proprietary. Therefore, we can't directly examine it or its values to assess the outcomes. In 2016, ProPublica obtained 2 years' worth of data through the Freedom of Information request, in which they assessed the data and outcomes for Broward County. This chart shows that reoffense accuracy was skewed when looking at race. Whites were consistently marked at lower risk for reoffending, while blacks were consistently marked as higher risk for reoffending. This illustrates that biases can be inherent in your data. In this type of post hoc examination of AI, several techniques can be used, including the intersection of variables and regression, which show how correlations are made. Here are another two charts that show the overall racial bias of the outcomes based on this algorithm. Again, blacks are consistently marked as having a higher risk scores than whites are. And judges openly disclose that they relied on the COMPAS risk scores even though they didn't have an idea as to the accuracy. ProPublica's analysts stated that they found the accuracy rate to be somewhere around 61%, which is virtually equivalent to guessing or flipping a coin. This example clearly shows why we must pay attention to testing for accuracy by an outside entity before we put any faith in an algorithm. This example also alludes to the fact that even though race was not used in the algorithm, the factors that were considered varied so closely to race that they were de facto proxy values. We must pay attention to the moral and ethical considerations of using artificial intelligence and putting trust in black box solutions, especially ones that are no more effective than guessing. So what do these examples show us? Well, number one, they show us don't settle for a black box solution. Just like our radiologist did, ask why. Performing a post hoc analysis on your data should have value, and even greater value when done by an outside team. Find out what the accuracy rates are. Using AI should increase your accuracy. Number two, there are analytical methods to assess your models. Today we showed you heat maps and intersection of variables. But it's far better to build in explainability from the beginning. Had the judges, in the case of COMPAS, originally known the questionable level of accuracy, they might not have relied on it. Number three, biases can be inherent in your data. Small training data sets are inherently problematic, as are training data sets that have unequal numbers of examples. You may need to prune your data significantly. In the pneumonia examples, the marginal data was readily available for the model to correlate. That could have been pruned. That would have led the model to only rely on the lung scans themselves. It may have increased accuracy. In the COMPAS example, we can gather that the factors used to create the risk scores were closely linked to race by performing an intersection analysis. Perhaps those should have been reassigned. Number four, always consider the moral and ethical questions of using artificial intelligence. Should we use artificial intelligence to evaluate people and dictate who gets a harsher sentence by our judicial system? And finally, many thought leaders in the field of artificial intelligence have stated that one of the most effective ways to eliminate biases from the beginning is to start with a diverse development team. I'm Dr. Kelly Carter. I'm a data scientist with CACI. Thank you for your interest, and if you have any questions, please feel free to contact me.